Hello everyone. Thanks for visiting my channel, Mr. Professor, or as we say in Korea, 교수 아재. Today, we are going to work through a beautiful problem from combinatorics and geometry. The question is this. If you place n plus 1 points on a circle and connect every pair with a chord, how many regions do these chords carve out inside the circle? We'll answer this by building a recurrence relation, showing that the number of regions A sub n satisfies A sub n is equal to A sub n minus 1 plus Fn, where Fn is a function we'll derive step by step. Let's get started. Let me set up the problem carefully. We choose n plus 1 point on a circle and draw every possible chord. That's n plus 1 choose 2 chords in total. One key condition, no 3 chords meet at a single interior point. This general position assumption just means we place our points carefully. We define A sub n as the number of regions those chords divide the interior of the circle into. Let's build some intuition with the small values first. And that's exactly what the next slide shows us. Before we derive anything, let's just observe what happens for small n. With n is equal to 0, just 1 point, no chord, 1 region, the whole disk. N is equal to 1, 2 points, 1 chord, 2 regions. N is equal to 2, 3 points, 3 chords, 4 regions. N is equal to 3, 4 points, 6 chords, 8 regions. N is equal to 4, 5 points, 10 chords, 16 regions. Now you might think, wait, is this just a doubling every time? 1, 2, 4, 8, 16. Looks like a 2 to the n. That's a very natural guess. But here's the catch. When n is equal to 5, we get 31 regions, not 32. The pattern breaks. So something more subtle is going on, and that's why we need to derive the recurrence properly. Here's the core strategy. Instead of counting all regions at once, we ask, what happens when we add just one more point? Suppose we already have n points giving us a sub n minus 1 regions. We add the n plus 1 point, which connects to all n existing points, creating exactly n new chords. Each new chord falls into one of two cases. Case 1, it doesn't cross any existing chord, so it simply splits one region into 2, contributing plus 1. And case 2, it crosses k existing chords, entering a new region each time, contributing 1 plus k new regions in total. Now the key question, for each new chord, how many existing chords does it cross? Consider the new chord from the n plus 1s point to some existing point, P. Look at the n minus 1 remaining points. Some lie to the left of P, some to the right. The crucial observation, a new chord intersects an existing chord if and only if that chord connects one point on the left to one point on the right. Same side chords never cross our new code. So if k points lie to the left and n minus 1 minus k to the right, by the multiplication principle, the number of crossings is exactly k times n minus 1 minus k. This holds for k from 1 to n minus 2. Let's see this concretely. We have n is equal to 4, 5 points, or chords drawn, 16 reasons. Now we add the 6-point piece of 5. So piece of 5 appears on the circle. We connect piece of 5 to piece of 2. To the left of a piece of 2, we have k is equal to 2 points, piece of 3 and piece of 4. And to the right, n minus 1 minus k is equal to 2 points, piece of 0 and piece of 1. So we expect 2 times 2 is equal to 4 intersections. What's the chord grow? First crossing, region count goes up by 1. And second crossing, up by 1 again. Third, up 1. Fourth, up 1. And the chord reaches piece of 2. In total, this one chord created 1 base and plus 4 crossings, which is equal to 5 new regions. So A sub 5 is equal to A sub 4 plus F5, which is equal to 16 plus 15. That gives 31, not 32. Now let's sum everything up. Step 1. The two chords with no crossings, k is equal to 0 and k is equal to n minus 1, each contribute plus 1 for a total of plus 2. And step 2. For k from 1 to n minus 2, the chord crossing k others contributes 1 plus k times n minus 1 minus k. Step 3. Summing over all n new chords, a sub n is equal to a sub n minus 1 plus 2 plus summation from k is equal to 1 to n minus 2, 1 plus k times n minus 1 minus k. Step 4. Simplify. The sum has n minus 2 ones plus the 2 from step 1, giving n total. So a sub n is equal to a sub n minus 1 plus n plus summation from k is equal to 1 to n minus 2, k times n minus 1 minus k. That right-hand expression is exactly Fn. The recurrence is proved. We can easily verify with a small values. You can plug numbers 1 through 5 into the formula, then you can get the values. So the recurrence correctly captures the drop-off from the doubling pattern. The summation, k times n minus 1 minus k can be evaluated using standard sigma formulas, but that's an exercise for another day. Let's recap the key ideas. First, the strategy: add 1 point at a time and count how each new chord changes the region count. Second, the two cases, no crossings gives plus 1, k crossings gives plus 1 plus k. Third, the counting argument. By the multiplication principle, k points on one side and n minus 1 minus k on the other gives k times n minus 1 minus k crossings. Putting it together, a sub n is equal to a sub n minus 1 plus fn, where fn is equal to n plus summation from k is equal to 1 to n minus 2, k times n minus 1 minus k. This is a classic example of the add one element and count the change technique. powerful tool that appeared throughout discrete mathematics. Thanks for watching, and I see you in the next one.